Now we shall compute the probability of error for integrate and dump filter. We know that sample output is x0t plus n0t. x0t is due to the signal component, n0t is due to the noise component. Now in transmitted pulse is either plus v or minus plus v. So based on this, yt is already determined as vt by tau plus n0t when xt equals plus v. So when the transmitted pulse is plus v, then output we already determined vt by tau plus n0t, and it is minus vt by tau plus n0t when xt equals minus v. So output polarity depends on the n0t. For example, our transmitted pulse is plus v, and if n0t is a negative one, if n0t is negative and it is more than this magnitude, that is, if n0t less than minus vt by tau, if n0t magnitude is less than vt by tau, then this addition will be negative and yt will be negative. So in that case, receiver will decide in favor of the negative pulse. So receiver assume that the transmitted pulse was the negative pulse, so there will be some incorrect decision. So in this case, there will be error. There will be error. There will be error in receiver decision. In second case, another case may be transmitted pulse is minus v and n0t is positive. If the summation is positive, that is n0t greater than vt by tau, then in that case this summation will be positive. As a result, yt will be positive. So actual transmitted pulse was negative, but output is positive. So receiver will decide in favor of the positive pulse. So in that case also there will be error. So these are the two conditions that receiver will decide some wrong pulse, and that will happen based on these two conditions. Now we shall see this in terms of probability density function. Suppose that is n0t axis, and this axis is corresponding to n0t. So if I draw the PDF, it will look like this. It is typical Gaussian probability density function with zero mean. Now n0t is vt by tau, so that is correspond to maybe this point, vt by tau, and n0t is minus vt by tau in this case, so minus vt by tau. Now this inequality shows this region n0t greater than vt by tau, so that is correspond to this region, and n0t less than minus vt by tau, that correspond to this region. So that is that region gives us the probability. We already know that area of the density function gives the probability, corresponding probability. So it is correspond to n0t, probability of n0t greater than Vt by tau, and this area is correspond to probability of n0t less than minus Vt by tau. Now we'll write the expression for the probability density function of the n0t. So we'll find the PDF of the n0t. Now we know that it is a Gaussian distribution. So f of n0t can be written as 1 by sigma root over 2 pi. This is standard Gaussian distribution expression, e to the power minus so that is standard Gaussian distribution expression, where sigma is the standard deviation and sigma can be computed as mean square value plus minus square of the mean value root. So sigma, we already know that sigma is standard deviation, which can be determined by mean square value of the noise, minus square of the mean value root. Now we already know that mean value of this noise is 0, so mx is 0, and this part we already computed, that is mean square value of the noise n0 square t average equals n0 t divided by 2 tau square. So we already determined this part. So sigma will be root over thus distribution function can be written as 1 by sigma root over 2 pi. So sigma you already know, that is e to the power n0 square t minus n0 square t divided by sigma square, 2 sigma square, 2 into this term square, so 2 into n0 t by 2 tau square equals 1 by tau by root over pi n0 t e to the power minus n0 square t divided by n0 t by tau square. So that will be the density function for n0t, and we need to determine the probability of the error for this case. So as we have already seen that if we transmit v, suppose we have transmitted xt equals v plus v, then error will occur if n0t less than minus vt by tau. That is, for this part, if xt is for this part, if xt is plus v, then if noise is more negative than this part, this n0t is more negative than this one, then error will occur, and that correspond to that region. So for this case, for this part, if we compute the area of this part, then we can find the probability of error. So that gives us the probability of error. So probability of error in this case, now here we have two cases. One is xt is plus minus v, and that is xt is plus v. So whenever xt is minus v, we need to determine the region where n0t greater than vt by tau. So the region is actually the area of this curve. So the area of the curve can be determined by integrating the curve over vt by tau to infinite. So remember, our curve was this one. This one was our curve, and we need to determine the area. So that area is actually PE, that area is PE, and we need to determine the area for the negative voltage in message. For positive voltage message, you can see we need to determine the area like so. So that was the density function, and we need to determine this relationship that is correspond to this area, and this can be determined by integrating. This area can be found by integrating density function over minus infinite to vt by 2. So that point is minus vt by tau. Now see, this part and this part are equal. This area and this area are equal. This happens due to the symmetry of this probability density function. So this PE and that PE both are equal. So we can determine any either of them. So probability of error can be determined by integrating any one of this integration. Next, we will find the probability of error for this integration. Now we will replace the f of n0t here in this any of these two functions. Let's consider this function, and that PE will be equal to vt by tau to infinite, and f of n0t we already determined this one, and that is tau by root over pi n0 t e to the power minus n0 t square divided by n0 t by tau square d of n0 t. So you replace this part. Now see, we cannot determine this integration directly, rather we will use the standard form. So we'll consider this power as y square. So this part is y square. So that is, we'll consider n0 square t by n0 t tau square equals y square, or y equals n0 t divided by or dy so we need this part d of n0 t, or d of n0t equals root over n0t by tau square dy, and we need to change the integration limits. Now as n0t tends to infinite, y tends to infinite, and second part is n0t tends to this one vt by tau, then y it will be root over v square t by n0. So once we replace these parts, we can achieve that PE equals and that is a standard integration that is correspond to error function. Now we shall use the standard integration into ERFC form. So in our case, that u is root over v square t by n0. So our integration 2 by root over pi 1 by 2 by root over pi root over v square t divided by n0 to infinite minus y square dy, it will be equal to 1 by 2 ERFC Now we know that v square into t is the energy, or you can write 1 by 2 ERFC root over E by n0. That is the PE for the integrate and dump filter. Now ERFC is monotonically decreasing function. So ERFC monotonically decreasing function. So as E by n0 increases, this probability of error decreases very rapidly, and whenever E by n0 is very small, ERFC will be 1 and probability of error will be 1 by 2. So that is the worst case scenario when the signal is totally suppressed by the noise. At that situation, probability of error will be 1 by 2, that is half of the times there will be incorrect decision.